Balls B and C are thrown up vertically. While ball B is launched with an initial speed of 20 meters per second, ball C is launched with an initial speed of 30 meters per second. Since ball C was imparted a higher initial velocity, it would definitely rise higher, so there is going to be some separation between the two balls. We are asked to find the separation between B and C after a time of 3 seconds. But we have to be careful here. Since they are thrown vertically upwards, they would both be accelerated by gravity, which would act vertically downwards, so in a direction opposite to that of their initial velocities. Let's go with the traditional approach first, using the equations of motion independently for both B and C. Let's take the blue ball first, and we apply the second equation of motion to this ball. Our origin is at the bottom at the launch point, so the initial displacement would be 0 and the final displacement would be the distance AB, which is unknown to us. The initial velocity is 20 meters per second as given, and the acceleration is in the negative direction, so it would be minus 10 meters per second squared. So ball B is thrown vertically upwards but is accelerating in the downward direction due to gravity. We are asked to find the separation in 3 seconds, so we are finding the displacement of ball B after 3 seconds, and we obtain that displacement as 15 meters. Now let's take the red ball, and we again apply the second equation of motion to this ball. The origin is at the bottom, which is at the launch point. The initial displacement will be 0, and the final displacement will be the distance AC, which is not known to us. The initial velocity is 30 meters per second, and this is given, and the acceleration is in the negative direction, so it would be minus 10 meters per second squared. So ball C is also launched vertically upwards, but is accelerating in the downward direction due to gravity. We are asked to find the separation in 3 seconds, so we find the displacement of ball C after a period of 3 seconds, and this turns out to be 45 meters. Knowing the displacement of the red ball as 45 meters after 3 seconds and the blue ball as 15 meters after 3 seconds, it is clear that the separation between B and C after 3 seconds would be 30 meters. Now we try and solve the same problem, but this time using the concept of relative displacement, velocity, and acceleration. So we follow the same steps as we had outlined in the previous lessons. Step number 1, we fix the frame of reference to B and pretend as though B does not move. So in fact, we are making ball B the observer. Step number 2, we obtain the displacement, velocity, and acceleration of ball C with respect to ball B. And step number 3, we plug the values of the relative displacement, relative velocity, and relative acceleration of C with respect to B into the equations of motion and obtain the unknown, which in this case is the displacement after 3 seconds. Now this is the appearance for the observer on the ground. Now let's see what this appearance would be for B, as B is now an observer who is not only in motion but is accelerating as well. Now ball B thinks it is at rest and measures the displacement, velocity and acceleration of C with respect to itself. The initial displacement of C with respect to B is 0 as they start out together. The final displacement of C with respect to B is the distance BC, which we need to find out. That will be the separation between B and C after a time of 3 seconds. The initial velocity of C with respect to B is 30 minus 20, which is 10 meters per second in the upward direction. The relative acceleration of C with respect to B would be 0, as both B and C have the same acceleration acting on them, which is minus g. So the relative acceleration between B and C will be 0, and since this is a constant, we could apply the equations of motion for C with respect to B. Think about it. Since the accelerations of B and C are the same, and we are looking at this from B's perspective, B thinks that C is moving away with a uniform velocity of 10 meters per second, and we have to find the separation between B and C in 3 seconds. So we could really work it out without pen and paper, and the separation in 3 seconds at a uniform velocity would be 30 meters. Since according to B, C is moving away at 10 meters per second. But let's substitute these values into the equation anyway. Now we plug the values of C that we obtained with respect to B into the second equation of motion. Since the relative acceleration of C with respect to B is 0, the last term zeroes out, and we obtain the separation between B and C as 30 meters in 3 seconds. So even though B and C were accelerating, since their accelerations were equal, the relative acceleration of C with respect to B was 0, and this simplified the problem tremendously when viewed from B's perspective. And you can see from the number of steps that the second approach was indeed less time consuming. Here is an interesting thought. Assuming that as B and C fall down, they don't hit the ground, but they keep falling, let's say down a cliff, B will continue to see C moving upwards with a uniform velocity of 10 meters per second without any acceleration all the way through the journey. If B and C were both moving with the same acceleration but had different initial velocities, then B would see C moving with a uniform velocity with respect to itself all through the journey.